Okay, so let's look at number 56. I think you guys need to see this one. All right, so I think almost everybody started it out right. So that was good. What was the parts substitute? It's obviously not partial fractions, right? So what was the u and the dv? Okay, so this is this. I think maybe one or two people forgot the chain rule. You got to multiply by the derivative of the inside, right? So you get that. So then the integral is equal to natural log 1 plus x squared times x. That evaluated from 0 to 1. Yeah. Minus the integral of x. So it's v du, right? So x times 2x squared is, or times 2x is 2x squared. Right there. Okay, so we should be able to evaluate this part. This is something I think no one got. So 2x over 1 plus x squared. You might see this in your partial fractions too. This has to do with what we discussed yesterday.
Can you just make u x over 1 plus x squared?
You could try that. That might work. I think that's that what you tried, Sam?
Or sorry, dv.
Oh, you're doing another parts thing? You could try it. I mean, you'd want to try some different things. You were talking this, right, Paul?
No. dv equals x over 1 plus x squared.
And then u is
2x.
that might, I don't know, that might work, but I don't think so. I don't think it ended up working. You could try a variety of things with this. You could just try u equals the bottom and then do a back substitution or something. But here's what you should recognize, especially since we're doing partial fractions. You're going to see problems in partial fractions that are like this. When the degree was bigger on the bottom, you could just go straight into partial fractions, right? If the degree is equal or bigger on top, what did we say you might try? Long division. Very nice, Brenna. So let's do long division and see if we can simplify this to something we know. I bet it comes out nice. Watch. So long division, let's do it. So I'm dividing 1 plus x squared by 2x squared, okay? Let's see what happens. So, oops. You need to turn this around, right? X squared, and then put your 0 in, like so, when you're doing long division. So 2x squared times what is x squared? 2. Maybe I'm dividing this wrong. I think I've got it backwards, don't I? You guys tell me. Do I not? Which thing should be dividing what? So we're trying to divide this guy by this guy, aren't we, when you say that? I think I'm backwards. Oops. So, dividing this guy by this guy. There we go. That works. Sorry. Okay, so x squared. What do you need to multiply x squared by to get 2x squared? 2. So then you go and distribute this back. So you get 2x squared minus 2. Yeah? And then you do your remainder. There's nothing here. When you do long division, remember you've always got to be really careful about this minus. So 0 minus negative 2 means the remainder is positive 2. Yes? So, how's that help us? Okay, so we've got this part that we need to do still. But now this integral has been simplified. This expression is exactly equal to the quotient of 2. Yeah? And what was the remainder? Also 2, but you need to express remainders correctly. Like if your teacher a long time ago said, you know, just put the remainder as 2 there, they weren't really right. If you were dividing, don't you have to put like if you had, let me just refresh your memory. What if you had like 81 divided by 8? Well, you figure out that the answer is 10, and you have a remainder of what? 1/8. 81 is 10. I mean, excuse me, 81 divided by 8 is 10 plus 1/8, is it not? So you got to do remainders correctly. So in our case, this fraction is the quotient 2 plus the remainder divided by that guy, what you're trying to divide by. Okay? That's no different than regular division. You guys did that last year. Why did that help us? Look how simple our integral is now. It's a lot easier. So I'm going to do this one, and then we'll do that integral. So if I put 1 in, I get 1 natural log of 2. Yeah? If I put 0 in, I get 0. It just goes away. So minus 0, there's that. And then this guy integrates to 2x. What's this integrate to when you distribute the integral? Imagine this was just a 1. What is that? Arctangent. So this is 2 arctangent of x. Yeah, if you had this right here and you pulled the 2 in front, it'd be arctangent. Okay? Then we got to evaluate that. So far we've got a natural log of 2 from the UV part, and then over here we're going to have 2 plus, what's the arctangent of 1? What angle has a tangent of 1? Pi over 4, 45 degrees, right? So that's what has an arctangent of 1. And then we got to go minus 0 plus, what's the arctangent of 0? What angle has a tangent of 0? Think about the graph. 0. We good with that? The graph goes through 0, right? I don't think about tangents with unit circle usually. So, anyway, so that really goes away. So we get what? Natural log of 2 minus pi over 2. That's the answer. Okay? So the main lesson here though is if you have equal degrees on top and bottom, this was one where I'd probably try to just do a U sub first, but it wasn't going to work. But if you have equal degrees on top and bottom or a higher degree on the top, you definitely want to use log division. And then you might need to do something else like parts or partial fractions, but okay? All right, that was a good one to start with, I thought. Okay, should we do like 2 more? I was thinking 2 more. You guys can stop me whenever you think, though. We didn't do one with quadratic factors yesterday, so let's see if we can find one of those. How about this guy? We'll try this guy and maybe do one more at the end of the hour. You guys help me set it up.
A over ax plus b over x squared minus x. So squares. We'll have an x.
There we go. See, don't just launch and do quadratic right away. It won't work, number one. You want to try to simplify as much as you can. This cannot be reduced. Can you factor x squared plus 4 no matter what? In fact, x squared plus 4 produces imaginary zeros, right? So that's an irreducible quadratic if it sets to 0 and produces imaginary solutions. This is definitely not irreducible. Paul said, hey, factor out an x, and you get this. So we've got 2 linear and 1 quadratic. So what's it going to be then? A over x.
Plus b over x minus 1.
Okay.
And x plus b over x plus 4.
We had no repeated factors, so we didn't have to worry about that this time. Okay? So then we're going to set up an equation we can solve for a, b, c, d. So it's going to be this. So let's just get rid of the integral for now. So that's equal. If you multiply by this common denominator, you get everything cancels. Well, not much cancels here. So you have an x minus 1 and an x squared plus 4. Here you have bx and x squared plus 4. Here you have cx plus d, put parentheses around it, and x minus 1. So crazy, right? So we can try to pick some convenient values to make this work. That might not be enough though. So let's see if we can start that way though.
0.
So Paul said, hey, 0 will make like those factors go away. So you put 0 in. Make sure you keep track of what you're doing. Write it down like a bullet point. So that goes away, -8. This Parker is not making me happy. And then if we put 0 here, we get -1. If you put 0 here, you get 4. Be very careful. 0 makes this go away. If you put 0 here, you get D. Oh, that makes that whole thing go away too. Ah, nice, because we got A now, right? So we lucked out. So that's -4A equals -8. So A is 2. Okay, is there another convenient value, or are we out? 1. I think that's nice. Let's see, so 2 minus 4, I'll just write it down. 2 minus 4 minus 8. This goes away because of right there. This is going to be B1 and 5. 5, am I right?
Yes.
You guys slow me down if you're getting lost. Put a 1 here and you get C
Cancels that.
plus, oh, it does cancel that out too. Nice, okay. So we get B then. Let's see, so what is that? -12 and 2 is -10. Oh, it worked out nice. So B is -2. Very good. Okay, any more convenient values that we can plug in? So let's keep note of this over here. A is 2, B is -2. We found those. Still got 2 unknowns though. So if there was just one unknown, we could just plug in any other value and we'd be able to solve for it, right? By putting these in. But there's 2 unknowns left. So you're left with 2 options. You can plug 2 more things in and set up a system of equations and use matrices to solve it. Okay, I'll maybe do that tomorrow. I'm gonna wait till Austin's here. He probably doesn't want to miss that. That's only if it's like really big. This one, there's another way also to get it. So let's maybe try to equate coefficients and see if anything comes out. So can you guys, in your notes, I'll give you a second here, can you expand this out? Like expand this out, get the coefficients on x cubed and x squared and all that stuff. Just make it as simple as you can, combine like terms, all that kind of stuff. So I'll give you a second, see what you can do. And I'm going to pause the video for those watching. It'll be on the next video when we finish. Okay, so this was a problem where equating coefficients might not have been the best approach. We'll do it another way as well. But this is the idea. You expand this out so you can see how I've expanded each one of these out. And then what did I do on this step down here? What did I do?
Yeah, coefficients and terms.
Yeah, so I looked at the like terms and factored in order to be clear on the coefficients, because that's what this is called, equating coefficients. So if I call it equating coefficients, what am I going to be able to, what information could I gain from doing this, which may or may not help us on this one, where we're going to have to do some more work. But what I found here is, we already found A was 2, right? Let's see if we can confirm it this way, that A was 2. So if I equate the constant coefficient on the left, which is -8, and the constant term over here, which only had an A, what do you get? You get a thing that says -8 equals -4A. Divide, there's your 2. Does that make sense? Okay.
So A plus B plus C must equal...
Right, so we know from this one that A plus B plus C must equal what, Paul?
2.
Must equal the coefficient on this side of that. Does that make sense? That's not very helpful because we only know a, so now we could like plug in a like you were saying, Brenna. Does that make sense? Which would only partially help us because we don't know it yet. But hold on. Okay, so we've got that guy. That's information we gained. What else do we know? Besides that one, if you equate x squared, what do you get? D minus a minus c equals the x squared coefficient was 0. Does that make sense? And then for this one, you have 4a plus 4b minus d. I hope I didn't mess that one up. Equals what? -4. Okay, and then we did that one. So let's say we already knew that a was 2, so we could fill that in on all these to maybe help us out. So we could say, hey, this is +2, so really the b plus c is 0. Yeah? And then over here, we knew a was 2, so if we have -2, then d minus c is 2. Yeah? See how we're narrowing them down? And then we knew that, what, a was 2, so that's 8. So if I subtract 8 on the other side, I get -12. So at that point, equating coefficients kind of didn't give us enough information because would we have had anything else? I don't think so. But doing it our other way, we also knew that b was -2, so let's put that information in and see if we can finish our problem now.
But we could also use those b plus c equals 0 and d minus c equals 2 for systems.
Yeah, definitely. You can do a system of equations at any point here when you need to. That's what the book did. They did a system. They didn't do my equating coefficients on this problem because it turned into a pretty ugly one, right? We'll do one more in a second. Which one you're talking about would be a good choice, Paul? Don't these all have different combinations, though? This has B and C. Does another one have B and C? No, if it did, we could do a system.
Find D in terms of C. Substitute.
We could find D in terms like here.
Yeah.
So Sam's saying D is 2 plus C, right? And then we could put that in for where?
The last one.
The last one. And then that would have B and C, and this one would have B and C, so we could combine those. Would that work? Yes, it would. That's creative. That's the way you got to think on these, okay? Let's just shortcut on this time, though, okay? Let's just remember that we knew B was -2, so we don't have to go through that work. And just put it here. Hey, now we know C is 2. Deal. And oh, now we can just put that here. So D is 4. And then we can finally do our integration, okay? So we'll do one more of these. That was probably not the best one to start out with, but still good practice. Okay, so the integral, coming back, put my dx on, that guy is equal to the integral of, oh, I erased them. You guys wrote them down. What, 2 over x minus 2 over x minus 1, those are easy, plus
2x plus 4.
2x plus 4, that sounds right, over x squared plus 4 dx. The first two are really easy. What's this?
Natural log of x. 2 ln x.
Okay, what's this?
2 ln x minus 1.
Watch out for chain mold on those. We didn't have one this time, but watch out. And then this guy.
A use of? I think might work. And if not,
It's so close. I think we need to split it. You gotta go 2x over x squared plus 4 plus 4, 1 over x squared plus 4 dx. So this one is a u sub, the derivative sitting right there. I guess I'll show it. So u is x squared plus 4, du is 2x, just like what we needed. So that guy's the integral of 1 over u. So it's going to turn into plus the natural log of x squared plus 4. You guys follow me? Brenna, Alexa, we okay? That's this one. I just split this one, yes. And then this one, what's this? arctangent. This came out and canceled here, so we have what? The arctangent of x over 2, but that's got a u sub, so am I going to do divide by 2 or multiply by 2 to compensate for that? I need to multiply by 2. Okay, so plus 2 arctangent of x over 2 plus c. Whew. There we go. That's challenging. That had a lot of stuff in it, right? We had to do setting up partial fractions. We had to do a more involved way to find the coefficients. And then we had to split this into a couple things that were a little tough for you guys to remember. So got a lot in it. Okay? I'm thinking we do one more, but I'm going to give you guys some time to work on a few.